Okay, can I start now? I'm not sure whether.
I'm looking to see if I can have your urban tribes.
Yeah, I can try later. I think it sometimes it works, sometimes not.
Oh, yeah, time for hilarious urban dictionary.
No, that's not me.
Yeah. Okay.
Okay, thank you for coming today. And this is actually a part of my preliminary exam, my talk for my preliminary exam. So it will be the work that I recently did in Adobe and finished and just got uh, got to the CVPR, and we are waiting for the results. So this is actually I have talked about this in I think maybe 2 months ago. That's my summer internship project. So a part of it will be familiar to you, but a part of it is new. So I'm sorry if you have seen any of these, but you can wait for some new things. Okay, so I can start now. The
So you're gonna talk for what, half an hour or so?
Yeah, I guess so. The length of 40 minutes is the length of the preliminary, but
Okay.
I'm not sure.
Okay,
Yeah.
you starting now.
Okay, yeah, I'm starting now. Thank you for recording. Okay, so the topic of the project is event-specific image importance, and these are the authors of this project. A lot of authors. First, I will introduce the motivation, and I'm sure you've seen this. So nowadays, it's more and more easy and much easier for us to take photos everywhere using our phones or portable devices. So we will have a large album in our device. But after that, if we want to, for example, make a photo collage out of this album, or for example, we want to select some important or more interesting images to keep, then we have to go through the hard manual process to select the important images or interesting images from this album and do the job. And this manual work is very tiring, very time-consuming, and very boring. So our motivation here is to free the human labor and to automatically do the photo selection or important image selection for a human. So this is our motivation. And before we start, I want to introduce the related background works for this project. So first large part is convolutional neural networks. It is a type of feed-forward neural networks. It is biologically inspired, and it is well suited for representation of natural images. And a lot of works have been focused on the basic computer vision problems, such as image categorization, image recognition, object recognition. But recently, there is a greater focus on higher level image property representation or training, such as event recognition and for example, attribute learning, something like that. And why this is related to our work is because our goal is to do event curation or important image selection, and we can think of that as another higher image property. And because of the great success of CNN, we want to use CNN for this job. And secondly, album summarization and photo selection is, of course, a very related work to our work, and it is also a well-studied topic. And there are mainly two factors that are considered when we want to summarize a photo album. First one is the single image property, such as image quality, image interestingness, image aesthetics, etc. And this is our event-based image important is one of the property here. It's a single image property. But besides this, another factor is also considered. That is the coverage or the diversity of the album. So this is an album-wise characteristics. But this characteristic is not considered in our problem, because in our problem we want to look for the image property or image importance for a single image, not the album. But our image important detection stuff algorithm can actually help with this summarization problem, because the image property, the single image property, is a very important factor in this problem. Okay, so before I start with the approach and result, we have to introduce our data. This is because currently there is no available data set for this kind of problem. So we have to create the data set ourselves. And we start from the Yahoo 100 million data set. And that data set has a lot of metadata. For example, the photo uploader, the time the photo is taken, and also some images contain the user tag data. And we segment the event albums based on the image, the timestamp of the image, and also the tag of the image. And after this, we randomly select 20,000 event albums, and that is our event recognition data set. And we have to acquire the event type label from this data set. So we use the Amazon Mechanical Turk, where we can hire some anonymous workers to label our data. And we have 23 available event types for the worker to select. And those 23 event types are the common event types that happen in our daily life. And those fall into 4 large categories. And after this, we have 20,000 labeled event event albums, and then we want to further create our curation data set for our job, for our problem. So we, because of the limitation of our budget, we select about 2,000 event albums, and those albums cover the 23 event types, and each event type has 50 to 200 albums. And we vary the number of album for each event type on purpose, because we think for some event type it's easier for us to learn something, but for some other event types it's harder. For example, we purposely select 200 wedding, which is the highest number for wedding, but we only select 50 for nature trip, because we think wedding, we can learn more from wedding, and it's purely intuitive stuff. And this is an example of our result of data collection. This is a wedding album, and what we did is we let 5 AMT workers to rate on this album, and for each worker, she or he needs to rate every image in this album, and he or she has 4 level rating, which are very important, neutral, or irrelevant. And after we got the 5 workers rating, we can average the rating, the scores from the 5 AMT workers, and this is our final ground truth that we use for training and test. So up to now, I guess you may have the question that whether our album is valid or whether this problem is actually doable. So our next step is to do consistency analysis on the data that we collect, and we use 2 measures to evaluate the consistency. First one is a Spearman's rank correlation, and the second one is Kendall's W. The first one, Spearman's rank correlation, is a common measure for the consistency analysis, and it's just a measure to evaluate the correlation between different raters. And the average of this correlation is 0.4 for all our albums. And the second evaluation method is Candles W, and that one is used. That one maybe not as popular. It is used for assessing the agreement among users, which is yeah. Now, Candles Tau is like another thing to evaluate the correlation, I think. But this one is different thing. And Candles Tau, I think, is to evaluate two. I think it's to evaluate among two workers. But this W can actually evaluate multiple workers, more than two. So this is very suitable for our problem because we have 5 workers. And it's not correlation, it's agreement. So it ranges from 0, which means no agreement, to 1, which means complete agreement. And our average Candles W is 0.4. So we can see that it's coincidence. Both of these are 0.4, and it's not a very high score for correlation or agreement. So in order to assure that this is really something significant, we further we further do the significant test on the Candles W for each of the event type. And here what I show is the 23 event types and their corresponding number of albums here. And in the parentheses is the percentage of significant albums at level 0.05, which is commonly used. And this is so this means that, for example, this one for wedding event, on average, there are 98% of albums that are significant if we look at the Candles W. And what I didn't show here is on average for all the 23 event types, the average percentage of significant albums are 86%, so which is quite high. And that means that most of our albums show a significant difference between, most of our albums show significant agreement among the 5 workers, although the agreement score is not very high, not as high as 0.9, 0.8. And also, if we look at the individual percentage of significant albums, we can see some interesting stuff. For example, the wedding has the highest percentage, which is 98, but sports game only has 58%, which is the lowest. And this is also conforms with our intuition that some albums is easier to learn because some albums, it's easier for human to agree on those albums, and the it's very clear what is important in that kind of event type. But for sports game, for example, it's very hard for people to agree on it because many images in the sports game album are really similar to each other, and it's really it's even hard for human to do that. So it also show that our selection for the number of albums is valid.
Wait, so
yeah.
What's the 98%?
98% of the albums are significant when we do significance test. Yeah.
0.0. Okay, so
0.05
or not.
Yeah, 2%
So
now.
You don't report here the actual average.
Oh yeah, I can also add that picture here. Yeah. You think that one is better?
How could it all be higher than 40? So.
You mean
One number to
I see. Yeah, sure. I can also show that. The trend for that one is the actual score is really correlated to this this percentage. Yeah, but if the percentage correlated, yeah. Okay, so after this, I hope I have shown that first, the event-specific image importance is highly subjective property. The second, people can agree to some extent on this property, and this is a valid problem for us to learn, to study. Okay, so finally, I will introduce our approach for this problem. This is our overall architecture for this problem. And here we use the pre-trained AlexNet as a starting point. And our approach, our architecture has several properties. First one is we use a Siamese architecture. Siamese architecture means that we have two identical parts in this network side by side here. So these two networks, they share all the parameters, but they have different input. So each of the part of this network take one image as input, and the loss function is also computed on the features computing from those two inputs. So this Siamese architecture is actually learning the relative properties from the input pairs, not from a single image. Yeah.
Did you try putting a hidden layer between FC7 and the score?
Yeah, I do, but it doesn't help so much because it doesn't help. It's a little bit lower than this one because I also try using different size hidden layer. For example, if I have the wedding has more hidden units, and the sports game has smaller, but that also doesn't help. So I guess I think it should help at some point if I try more and see what is the best.
Did you regularize it?
Yeah. The regularization is like naturally included in the cafe. Yeah.
Sorry, Yufei, what's the loss function?
Yeah, that's like the first property. So
Yeah.
you can just wait for it.
Oh, got it.
Yeah. So this is Siamese architecture. And second property is we have feature sharing among the 23 event types, and this is illustrated here. So our final goal is to predict the image importance score for each of the event types separately. But here we are sharing the network actually is trained on all the 23 event types except for the last layer. Here, the last layer is the score prediction layer. So definitely, it is not shared among the 23 event types. But all the feature extraction part are shared for all the 23 event types. That means they are all jointly trained on all the data. And this is because we have two reasons for this. First is there is a strong visual similarity among different event types. Although the albums are from different event types, the natural visual properties are almost all the same. So that's why we want to share all the visual features among all the event types. And secondly, because we have a relatively small data set, we want to reduce overfitting as much as possible. So here the feature sharing can reduce the number of parameters largely, so that this is a regularization of our network. Oh yeah, third. So the third property is our loss function. And we design a loss function specifically for this problem, and we call it piecewise ranking loss. And it has three conditions. So the conditions are about the MS and MD here. MS and MD are two predefined margins. And here the DG and DP are respectively ground truth score difference and predicted score difference. So the three conditions are if the ground truth difference from the two input images are smaller than the threshold, that means if they are similar, or if they are larger than another threshold, that means they are dissimilar, or if they're in between, that means they are somewhat similar. So when they are similar, that means the DG is smaller than the MS. our rank loss is a variation of the contrastive loss, which is used in the Siamese network. That means when they are similar, we want to push them together, pull them together. Push them together. Yeah, push them together. Sorry. And the third condition here is when they are dissimilar. They are when the difference is larger than another threshold. That is similar. This loss function is similar to contrastive loss when the input pair is deemed dissimilar, and this means we want to push or pull them the pairs apart as far as possible. Actually, not as far as possible, but larger than a threshold. And this is also similar, a variant of the SVM rank hint loss, but this is an L2 loss, not an L1 loss. Oh yeah, but here the GP is always positive because I didn't show it here, but GP is always positive. Yeah.
Do you have references for this? Because I asked them to do a computer vision paper that does this, and I think it has to pull things together.
You mean just rank SVM and yeah, sure. Consider that. Thank you. And the third part here in the middle, the second part in the middle is when they are somewhat similar. We want also to pull the predicted score difference into the same range with the ground truth score difference. So we want to make the prediction as close as the ground truth, but we also have a margin here, so that because our ground truth is acquired from human, and this is a very subjective problem. So there is a large variation among the human raters. So we want to make the network more stable with this kind of high variation ground truth, and that's why we have the GP and we have the MS and MD here. It serves like a relaxation term or a slack term. But what it does is just to push the difference together, to pull the difference towards the ground truth difference. And the reason why we are using this, or the advantage of using this, is first, it can be trained on all possible image pairs, even though the two image pairs have the same ground truth score. And this is different from the SVM rank loss or the contrastive loss. Actually, contrastive loss can also use this, but it doesn't think about the somewhat similar stuff. So the first advantage is over the rank SVM loss. And the second one is, as I mentioned, it introduced a relaxation term, the MS and MD, so that the network can be more stable when the ratings are subjective. And this is in our case. Okay, so finally,
Can you tell me what happens when they have the same?
Yeah, just first one? You mean,
So DP is the predicted score difference.
Yeah.
Where does the ground truth?
Here, in the condition.
Oh,
yeah.
Right. Okay, so if the ground truth is 0.
Yeah, then the DP should be.
Then we do the top.
Right.
And that one makes the score closer
together, but it doesn't penalize when they are close enough. Yeah, but I have absolute value here, so if the sign is different, it doesn't matter. Okay. So finally, the first property is we use a two-stage progressive learning. Yeah.
If the sign is different, it doesn't matter.
Sorry, what was that?
If the sign is different, it doesn't matter.
Yeah. So this is just like a slack term, because if, for example, if not doesn't matter, but if they are really close to each other, for example, the first has a score 0.6, the other is 0.5. The prediction is the other way around, 0.5 and 0.6. Although the rank is different, but they are still similar, because this is like just to take into account the variation among the workers' rating. So it still doesn't penalize it. But if they are really different, if the MS, if the difference is larger than MS, then it will penalize it.
Okay, but will it always penalize it in the right direction? If you use the absolute value?
Yeah, of course. If, for example, if they are, if the sign is wrong, it's still pushing them together. Yeah. Okay, so this is because if we directly train the CNN for separate event types, the problem is, although the feature is shared among the 23 event types, the last layer, the final prediction layer, is not shared. It's trained separately for each event type. And that may lead to overfitting for some event types with less training data, because we have a relatively small data set. So therefore, we use this two-stage training process. First stage is we train all the image pairs with one output for all the event types. That means we give no event type information to the network. And then at some point, we switch to the training with separate output for each of the event type. That means we, at some point, we add the event type information into the network. We actually also try to cluster the event type into K superclasses according to their similarity, so that we can leverage the similarity relationship between the event types. But we find that doesn't help. And my guess is maybe our algorithm for the clustering is not as good, and this need more to explore.
So for similarity, you use the FC7?
Yeah, I use the, as you suggested, first I predict this importance score for each image in the album, and then I get the rank, and I calculate the Spearman's rank correlation, and I use
the clustering.
Oh, yeah, that's the clustering. Now I'm clustering the event types, right? So for each event type, for each album, I can assume it being in the 23 different event types. And for each event types, I can input the album into my network and get the rank for each of the album, assuming it is in each of the event types. Yeah, and then I can calculate the Spearman's rank correlation between each of the event types.
That doesn't make sense.
That's what you suggested. Maybe you
No, I don't
didn't.
think so.
Yes.
I don't think so.
Yes.
It doesn't make any sense.
Why is that?
Why would you cluster them based on their ranking?
Yeah, not ranking, but rank correlation. That means if for example, if I think this album is a wedding.
You
Yeah.
cluster them based on.
The rank correlation score.
Right. So
Right.
how birthdays would rank it versus how.
Yeah. That's it.
Okay,
That's it.
I see.
Yeah, but we can try different clustering method and see
Yeah.
what happens.
Okay, that's a weird idea. Yes, I have.
But that's very easy because I can calculate the rank correlation very easily.
Right.
Yeah.
Okay.
Okay, so yeah, so this is the end of the approach. Then I want to show many results comparing our result with many different baseline methods. But before that, we have to decide the evaluation matrix. Here we have two. If we think the top T% images in one album as relevant images, remember this hyperparameter here. If we have a T here, then we can have two different evaluation matrix. First one is the mean average precision, which is commonly used in the retrieval community. And that is basically the average area under precision recall curve over all albums. It's really complicated, but basically, if the score, we want the score to be as high as possible. And second is the precision. And this is the ratio between the number of relevant photos in our retrieved images and over the total number of relevant images. So it's just a ratio at level T. And also the maximum possible value for this is 1, and we want it to be as high as possible. And here is the result. So in the left columns, this is MAP over T%, T varying from 5 to 30, and the right columns are the P over T%, T varying again from 5 to 30. And I will explain the comparisons one by one to you. The top two ones are random and worker. Random means we just randomly pick the top T% images from the album, and that is a baseline method. And worker is if we evaluate single worker, this is like what human can get. And first, aesthetic. This is because in some literature,
So
yeah.
So the worker one, you're ranking one worker against the other 4, or what?
No, what I did is one worker as the other, not the other 4, but all the 5. So it's like kind of cheating. But after this, I can compare this to the,
You see how well one worker is correlated
with the ground truth.
with all 5 workers.
All 5 workers.
Include that guy.
Yeah. So that's kind of cheating. So if I exclude that worker, it will drop. But I think it's not fair to compare that to all the other, because all the other are rated upon the 5, the ground truth that is evaluated on the 5 workers. Yeah, but it's just like here to show what this worker can do. Yeah.
And that's the average overall.
Yeah, average overall 5. The reason why we include aesthetic here is because in some literature, people show that our when human is going to select some important images from an album, they tend to use aesthetic score as one factor. So here we want to see whether this is a really important factor or not. And the result shows that it is just slightly better than random, and it is not very important.
Did you ever say how you do aesthetics?
Do you think I need to say
Yeah,
here?
I mean, somebody's going to say, what?
Okay, so aesthetic.
Get that.
Yeah, so aesthetic is. I forgot. I think they use. Yeah, I'll check. They use CNN method. They use CNN method to evaluate aesthetic, and the aesthetic scores. They have a data set for the ground truth aesthetic score that is labeled by 5 to 10 workers. I'm not sure. I will check, and then they use that to train a CNN to predict that.
So it's how beautiful it is.
Yeah. Or I don't know, appealing. I think aesthetic doesn't have. I think beautiful is not the only criteria. Anyway, yeah. And then we want to show, we want to see whether the pre-trained convolutional network features can be used for this problem. So here, the pre means we use pre-trained CNN features, and we use k-nearest neighbor search. That is our first method, and we also use rank SVM. That is our second method. Both methods can show that the CNN features can actually generalize to some extent to this problem. But again, it's not as good as our method. So that means the pre-trained fine-tuning can work. And we also show.
Did you ever say fine-tunes?
I don't think so. Yeah, I'll add one. So we after the.
How much does fine-tuning improve things?
So if you compare the pre-SVM and SVM CNN, I think that's how it improves here. It's like it's smaller in the beginning, but larger.
But the SVM CNN is pre-trained.
It's not pre-trained. It's rank SVM.
Is
What were the features?
Sorry, is that?
It's fine-tuned.
Yeah, that one is fine-tuned.
Okay.
Sorry.
It's fine too, but it has the features from the just
It's yeah, it's fine-tuned on our dataset, but it's pre-trained on ImageNet, the AlexNet. Yeah. We actually also tried the VGGNet, but it works actually worse than AlexNet. And we also want to find out whether Siamese architecture can help. So this is a comparison. The Euclidean means we train a single network for single image score prediction using Euclidean laws. And we can see that it is consistently worse than the SVM when we use rank SVM, especially when, where is it? Yeah, especially when T becomes larger. So that means Siamese architecture really help.
I don't know.
Oh.
It looks to me, compared to the SVM, not sure I'd call it. You'd have to do statistics on it to see whether it's really.
Okay. Yeah, because I don't have so many rounds of tests, so. But if you see that, it's really it's becoming larger and larger.
Yeah, but you also care about the smallest T. The most.
Yeah, like the first one, right? Yeah, I guess so. But I think this part is more important, like the 10 to 15 stuff.
No, in the paper you say you care most about 5.
I really don't think so. I care when it's smaller than when it's larger. Yeah, and also if we compare the rank SVM loss with our piecewise ranking loss, we can see that our piecewise ranking loss can achieve better result, much better result. That means piecewise ranking loss is really helpful. And also we want to find out whether our two-stage progressive learning help. So we have three-way comparison. First one is if we give no event information into the network. Second one is if we directly give the 23 event type information into the network. And third one is if we use the two-stage progressive learning. Then we can see that, again, our progressive learning can overperform steadily, I guess, than the other two. So that means the two-stage really helps. And finally, our best result is achieved with an ensemble of 5-fold cross-validation networks. So that's based on the progressive learning, but it's the ensemble of 5 different networks. This is our best result. Okay, then I have some, I guess, more beautiful results. For example, this one. I compare our result, which is the red bar, with 5 or 6 different baseline methods,
So
and also the
you
worker.
can barely read it. We certainly can't.
You don't have to read it, I think. It's just, it's,
No.
really?
No.
Okay, I can make that larger, I guess.
You need to embiggen that.
Okay, so that's just 23 different event types. These are 13 event types. These are, I guess, 10 or, yeah, this 12 and 11 event types. But if you just ignore the actual event types, you can see that our result, the red bar here, consistently outperform all the other methods, except for several outliers like this. But most of them, at most cases, our result is better. The outlier, one of them is nature, the other is architecture, and protest, I guess.
What wins there?
In architecture, Euclidean wins. In nature trip, oh yeah, this is interesting. In nature trip, although aesthetic, if you remember, aesthetic score doesn't help for most of the cases, but in nature trip, aesthetic is the best.
So another thing is these colors are very close together.
Oh, really?
The two blues look identical from here.
You mean
Yeah.
the dark blue, or this one? This one is black. You mean the black and blue?
It looks blue.
Oh yeah. Oh yeah, it's blue. It's darker blue. Sorry, I will change it to black, I guess.
And the two reddish ones look identical.
I mean, oh yeah. Yeah.
Almost.
Sure. Yeah, it's clearer now. Here, but okay, I will change the color. But that means that aesthetic is really useful in some cases, especially when it comes to the beautifulness of the images, like nature trip. And finally, I want to show some real results that we can achieve with the photos, the albums. So this time I won't let you to guess which one is better. So the first, there are 3 rows.
You should make your committee guess.
Okay, but I have 5 images. I guess they will get tired after 5 images. But yeah, I can show 3 or something. Okay, so
Make it possible to have them guess.
Okay.
See how much fun.
Okay. Okay, so here all my results are arranged like this. First row is ground truth, second row is prediction, and third row is random. And this is from one single album, and this is showing only top 15% of the images retrieved from this large album. So you cannot see the whole album here, but you can guess the average quality of this album from the random selection. And I guess you can see that how our result correspond to the ground truth result. Also, how the random result is random. And this is a wedding, and this is a show, a parade show, a parade. And again, the last is random, and it has some random, random selfie, random ground, I don't know, stuff. But yeah, you can capture some better results, because top 15% of the random should be in the top 15 in the ground truth actually. And this is graduation. And although random has a lot of shots which is taken from a very distant place, but these kind of images are not preferred by our people, by our workers. So our result will like eliminate those images. Yeah.
So in your training stage, you have image, you have paired image
Yeah.
into the network.
Oh yeah, I didn't I didn't show it here, but in the test stage, okay, I guess I should explain that. So in the test stage, I just like cut the network into half and use that, because here this is a score prediction. So if I only input one image into this half of the network, then I can get the prediction, just directed prediction of score in this stage. But that prediction, that score prediction, is not the absolute value of that score. It only makes sense when you compare it to with the other images in the album. So finally, actually, we are not really predicting scores. We are predicting rankings.
So your output is the score.
Yeah, our output is a score, but we are not comparing the scores. We are just we just rank the images and see how the top retrieved images correlate with the ground truth. That means if you compare the ground truth score with our score, just single score, then it will be very different, because we are not training on the single score here. Yeah, I guess for the sports, although all the images look quite similar to each other, but if you look into the random images individually, you will see that our prediction can capture some very exciting movements from the players, I guess, not something like this. And finally, there is a result from the theme park event, and our prediction favors the shot with the characters in the theme park, and it also highly correlates with the ground truth. Okay, if you want to see more, I have more. I have like 60 of them. And finally, the conclusion and future work. So we have several steps. First, we introduced a new image property, which is event-specific image importance, very long name. And second, we provide a new data set to study this problem. And third, we show with the data set that this property, this event-specific image importance property, is highly subjective, but is still well-defined and predictable. And finally, we propose a CNN-based method, and our proposed method can outperform various baselines as we compare. And this is the conclusion of our work, and we can have many possible future works to do. For example, we can further investigate the relationship between different event types and to use that into our prediction. And also, we can develop a curation system that is based on this image importance score, but also consider the take the album property like the coverage and the what's the other? And diversity into consideration. So that's to develop some system based on this image score, as I mentioned in the beginning of this talk. And then that's it. Thank you. And do you have any questions?
Yeah, so can you explain what was the training?
Oh yeah, sure. Yeah, I think that is really similar to what you are doing now. Actually, I was inspired by this because when I try the training with no event, I see that it is quite the score. Where is that? Although the score is not as good as this no event CNN, although the score is not as good as our training method with directly using the 23 event types, it's quite close sometimes. It's quite good, the result. So I think if I can combine those two together, maybe I will get better result. So here what I did is, what I did is first I trained all the image pairs with one output. That means here I only have one output, not 23 different outputs. And I view all the training image pairs from one single event type that is like a large cluster that contains all the 23 event types. And then after some point, when the algorithm converges, then I split the final layer into 23 different event types like this. And then I didn't mention is I copied the because all the layer that is before the final layer can directly copy into the new network. But what I also did is I also copied the final layer into the separate 23 different event types. That means I initialize the final prediction layer with the one that I trained from no event type.
So train 23 different kinds of this carrier method before you change the final layer? 23.
No, not 23, but one, because at that time, like in the first stage, I give no event type information, and I view all the 23 event types as a single large event type. Yeah, so it's like all the predictions for all the 23 event types are the same, not the same. Yeah, because in the first stage, for example, the last layer is 4096 by 1, and then here is 4096 by 23. Then I just copy paste. It's just like expanding it to every dimension. Yeah. So I also, before this, I did the experiment without copying it. it doesn't help so much. So that's why. Because I think that's why, because here I'm all the layers except for the last layer is already shared when I train the second stage. So the last layer is the layer that I can get more improvement. So I have to initialize it with some valid value. That's why I did this. Yeah.
So that was almost exactly 45 minutes before
Yeah. So
Andrew's question. So I think that's good.
so you think I don't have to include or I can make this shorter, like maybe cut the data collection part, something like that? Or do you think I only need to? I think I'm fine with only talking about this one. I don't want to talk about the urban trap actually.
Yeah. Okay. Yeah, Andrew.
It's fine. And also, do you think I need to include like more detailed related work here, like how the CNN is, how the CNN architecture is like, something like that?
Well, the main thing you did, I mean, you did a lot, but the novel part here is the piecewise ranking function.
Yeah, I guess so.
So you might want to put up what the standard
SVM
ranking
Okay.
loss function is, and
Okay.
say why yours is better.
Okay. But so I don't need to like explain the convolutional layer here in the convolutional network, because Nuno definitely know that, but I'm not sure about Professor Baskerville. But
Well,
I think
should.
he should know. Yeah, I think he should know. Okay.
Yeah, I think personally I would explain like, the ranking loss first. And explain
Okay. So you mean like for when I talk about this before this, I can. Okay, the normal rank loss. And also, something interesting to me is I tried the rank loss with L1 and L2, and what I find out is L1 it works better than L2. But a paper that I saw mentions that L2 is better than L1. So I'm kind of confused. I'm not sure which one is better than the other. Oh, really? Okay.
But again, like I don't want to just spread
You mean?
what like it's maybe we should talk about this offline, but like if you're training on a classifier,
Mhm.
you use a regression as a classifier, right?
Mhm.
You can also just use calculate each loss, but then square it. You have a gradient stage.
Mhm. Mhm. Yeah.
But that should be very similar to L1 as the thing, but it's different from using the regression as a class. Basically, everything that I'm doing is using
Yeah, I know.
using logistic regression. Otherwise, doing the same thing.
Yeah.
Ology and then
Yeah, sure. I think so. Yeah. Okay, we can discuss. That's fine. And thank you. I think that's it.